So today I will give a talk on the Ossel's theorem. It's a theorem that proved by Valentin Ossels in 1965, and it was presented on the ICM at 1966. So let me start. Oscillated, yeah. So I'll start with briefly recall some definitions. So I start with one second. I start with recall of the Birkhoff-Pointwise theorem. So we say that we have a transformation T that acts on omega space with measure mu, which is ergodic probability measure, ergodic probability measure preserved system. And let we have some function, integrable function f. So for almost every omega from big omega space, we have the limit of the. So we have the point, we take the orbit, and we want to see the average and the average value. So this converges to the integral of space f d mu. So this quantity on the right is the space average of function f, while the quantity on the left tells us about the time average. So to move forward, I want to give an example. So we have the smooth manifold M, and function f that provides from M to M. And this is a smooth dimorphism that preserves measure M. And we want to take the derivative. So this means so this is the linear map, and in analogy with the Birkhoff theorem, one we can infer about the asymptotic behavior on the end manifold composition. So this gives our composition that goes from the Euclidean space in the point P M to the Euclidean space with when they apply the big F function n times to the point on this manifold. So the answer is of this is given by the oscillated multiplicative theorem. So the definition I should recall this about the cocycles. So we have the transformation T from omega to omega. And we have the vector bundle on it. Then V is a cycle, right? Over T, such that if the action of T leads to our vector bundle V by linear transformations. In other words, we have in the fiber, we have the linear transformation that goes from the vector bundle on the with the fiber of omega to the vector bundle. Then when we moved the R point. So for the simplicity, we can tell that it is invertible transformation that we reach smoothly with omega. Да. У нас есть как раз таки transformation из омега в омега. То есть у нас вот у нас была омега, и на ней у нас векторное расслоение. Мы переместились вот сюда.
Ага, это Т-омега.
Это вот мы Т-омега. Просто может быть путаница в том, что это Т-омега. Здесь индекс говорит о том, что мы точку омега отправили в какую-то другую точку. И над ней есть расслоение. А это говорит нам о том, как мы будем действовать вот отсюда вот сюда, между расслоениями.
А что вы про омега предполагаете?
Ну, это должно выполняться для почти каждого омега, то есть это просто точка из...
Омега большое.
Омега большое, это у нас probability, это пространство с вероятностным мерой и трансформация, которая ее сохраняет.
Нет, просто а что такое пространство, если вы рассматриваете касательное расслоение над ним?
Оно касательное или векторное?
Или какое-то векторное?
Оно векторное расслоение.
Какое-то, но все равно вы рассматриваете векторное расслоение, да?
Да.
Чего вы требуете от этого пространства?
Ну, вроде бы ничего не требуем.
Может, мера Борелевская все же?
Мера борелевская, да, конечно.
Нет, но вам не нужно, чтобы оно многообразием было.
Ну, сейчас.
Можно же векторное расстояние на просто логическое пространство определить?
What is the meaning of a vector bundle?
So we can briefly call this smooth manifold, and it will work out. But in the but
Okay.
I think this is we don't have enough. We don't restrict what is our omega space, but it definitely work out with some smooth manifold.
Не очень понятно, потому что если у вас есть отображение базы омега всегда, и вы хотите получить согласованное с ним отображение слоя, вам что-то нужно предполагать про гладкость многообразия, про гладкость отображения. Для Линии этого недостаточно.
So in the article that I read, we only say that we have good enough gluing transformation, gluing. Second. В общем, скорее еще отображение. Gluing maps.
Okay, just continue.
Okay. So the example that can motivate oscillator theory I have a matrix A that acts on the N, and this matrix have a positive n values, exponents of lambda 1, etc., to exponent of lambda k. So maybe they have the multiplicities, and for a typical, and we take the typical vector of Rn, and we want to find out the behavior of how it grows when we apply the matrix. So for typical vector, our growth rate will be as n getting large, will grow with the rate exponent n multiplied by lambda 1. Еще раз? Это мы просто... Не, это мы просто матрицу А применяем n раз.
То есть А у нас...
Да, это matrix. So we have the transformation on Rn, and we want see how act.
n большой с n малым совпадает.
Еще раз.
У нас просто n малое, я поэтому...
Нет, не совпадает.
То есть
Нас интересует, когда мы будем увеличивать n, как себя будет вести вектор v. И говорится то, что он будет стремиться вот к такому значению.
В мы откуда взяли? А в мы откуда взяли?
V это... Мы...
Что значит стремиться? Ну, это же, если n, например, идет если лямбда 1 положительный, и n, например, стремится к бесконечности, то это справа же до бесконечности.
Здесь оно... We say that the typical vector, and they behave when n gets large, then we have the norm that behaves like that. So what I want to say is that
can be formulated as that the root of x power from the left side tends to the e raised to the lambda sub 1, or it means something else. Because if so, we have a sense in this tension, but now the right side tends to 0 or to infinity. It depends on sign of lambda. With something else, it is not interesting, but it's strange limit. I mean, could you please write what do you mean by this tending to the somewhere?
only thing I can say that it's So with the typical vector of R, it is behave with eigenvalues like this. It's positive, and we have the limit. No. Let me continue, and in the theorem it will be more precise. And but if V contained of the span of eigenvalues with eigenvalues like e to the power of lambda 2, we have that we have the growth rate of this will be different, and when we repeat the analysis, when we have the V that lies in the span of the vector corresponds to the exponent of lambda 3, 2, and etc., we have the sum of the filtration of our space. Это собственное значение. Ну, в целом вот это собственное значение. So, let me state the theorem.
Sorry, one more question. We have the limit, but if I take a lambda where instead of V as in your formula, I will have other limit which does depend on lambda which I times to V. I think should it be the A raised to the n of V and over normal V, or it isn't shouldn't be here because it's look very strange because I can consider for instance.
It is so let's say that with enough large enough n, we will get the growth rate like this. Okay?
Okay.
So the oscillated multiplicative theorem So as I mentioned earlier, we suppose that we have some vector bundle V, and our space, Borel sigma algebra, our measure mu, and the transformation T. It is cocycle over an ergodic probability measure preserving system, and assume that we have the V with equimetric on each fiber, such that our operator name, oh, sorry. The mu is like the infinity, so which want to say that our operator not do some complicated and wide stuff, so is quite simple. And the logarithm plus is the maximum of the value and the zero. And by the so this is the operator norm of a linear map between two norm spaces. So if these statements are applied, we can say that there exists real line numbers логарифм с плюсом, логарифм плюс, оператор, ну, интеграл. Где логарифм плюс — это максимум из значения и нуля.
Ага. Сейчас еще раз. И получается, можете вот расшифровать? То есть там норма Т.
Норма от оператора Т омега, ну, интегрируем по мере. Дальше я это именно, далее я это обозначу, но у нас есть над каждым слоем свое отображение. Так, so we have we say that real numbers exist such that lambda k and lambda k may take value minus infinity, perhaps. And we have the T invariant subbundles of V defined for almost every omega from our space, so that I will say what is it 1 minute later. So we define such subbundles as if we take such that if we take the vector v. Сейчас, я вот как раз таки хочу сделать. А где? Ergodic probability preserving system. So, we take the vector v from that lies in the sum bundle E, but not lies in a smaller sum bundle. And this with the property that if we have the limit that n goes to the infinity, 1 or n, so the so we here the state that we have the vector from some subbundle that not lies in the smaller, that we know that the growth rate will be this number. This lambda E called the Lyapunov exponents. So the small remark, we can assume that our transformation is T is invertible, and by the здесь будет хорошо видно? So we take the invariance of the subbundle lambda e means that the invariance means that we have T omega that goes to the linear transformation goes from the V omega to the V T omega, and takes our subbundle V omega with less than lambda e to the subbundle that is less or equal than lambda e to the T omega. And for this filtration, we will call the forward oscillated filtration. Also, that I mentioned the numbers called the Lyapunov exponents. And the multiplicity of our Lyapunov exponents and the E, it is just, we take the dimension of vector subbundle that less or equal to the lambda E minus dimension that is bigger. So this the dimension of the subbundle that have less or equal lambda E plus 1, lambda I plus 1. So let me continue here. So if we suppose that T is invertible and cos cycle V also satisfies this assumption, we will change our forward filtration to the backwards. So let me state this. So we can apply the theorem, and we can get the set of new exponents. Exponents new I that we have to call the backwards oscillated filtration, like this. And by construction, if we take the vector from V subbundle V as let's call new it without vector subbundle nu g plus 1. And if we get the intersection, so for this state we can say the same result. Will be too small to write here. So to continue this sentence, we have the vector from the some bundles, and the state of the theorem in this case will be that we have the limit that n goes to the n large goes to the infinity. We take the average of logarithm norm t minus n v. So, and this goes to the nu g. Okay. So we can define the subbundle v lambda g. We define it as v less or equal lambda g, and this intersects with v subbundle v with this exponent. So if we take the backwards filtration, the numbers or the Lyapunov exponents will be the same, but not the bundles. But if we intersect the right bundles, we can get this subbundle lambda g, and now we have it gives us the invariant direct sum decomposition of v. So it will be 0 to k. So now I want the state, the connection between the oscillator theorem and the Birkhoff's theorem. It is equal if we by our bundle V takes the one-dimensional. So let me erase here. Hmm?
It's one-dimensional.
Yeah, if we take the dimensional vector bundle V, so the oscillator's theorem have equality with the Birkhoff's theorem, and I will show now. So V is one-dimensional, and we define the function f from omega as logarithm approximation in the fiber of omega with vector v and with the norm of vector v. So yeah, and it's not the zero vector. we can write the sum like this.
Получается, у нас v берется произвольный.
Сейчас скажу. Не совсем произвольный. V lies in the v omega, in the fiber. So,
Мы берем произвольный из v omega.
да. And so this is the transcoping series. So the result is 1 over n. No t n v over v, and the Birkhoff's theorem gives us that converges to the integral of f mu, and we can call it we can call this as our lambda. So the Birkhoff theorem gives us this number, and is C. We can see that is also, and the oscillator stem theorem gives us also this lambda. Okay. Now I will erase all the notions. And we prove the oscillator theorem via two lemmas. So our goal is to take the some bundle, or we want to take the bundle of our V, and we want to decompose and construct such filtration. So, the first lemma so at least one of statements is true. So, the first statement, there exists the lambda, and such that for almost every omega from our space, and for all non-zero vectors from V omega, we have that the limit that takes, so our vector grows at the rate of lambda. And this limit is uniform if we take the vectors with it is uniform. if it is uniform. It is uniform if we take the vectors with the norm 1. And the second statement is that there exists not exists non-trivial proper T invariant subbundle bundle E. When we say the proper, we should say we mean that its dimension bigger than 0 but less than the dimension of V. So which is defined at almost only omega. In other words, either we can find either the vectors in our space will grow at the same rate, or either we can find the bundle, we can find the subbundle with the proper subbundle. And the second lemma is we can lemma 2. We have to consider short exact sequence of our cocycle over omega, our space omega, that we have so this are the short exact sequence, and we can assume that there exists our exponents for this all invariant, this and this invariant. So we can find the exponents lambda E and lambda F such that for almost every omega from our space, we can state that for every vector from our space E vector from the space E that not equal to 0, and we have the so the growth at the rate of lambda E. Same for the space F. For F from F. So, of course, the limits are uniform if F and D with have norm equal to 1 for a fixed omega, and this and same for F. So we show that in these two invariant spaces we have the vectors, and we have this for E, and we have the same for the F from the F. So, and it's not the end.
Sorry, but in lemma 1, the two statements are not contradictory, yeah? Those can be...
Yeah, they can hold both at the same time. Of course. One sec. So, let me continue. The second lemma, if lambda e is bigger than the lambda f, we can find the splitting map, the linear map that splits. So this map is sigma from f to v, such that our bundle v splits in the direct sum of e and the sigma of f. And we have the p right here. And p combined with sigma is the identity in the f. Of course, and its composition, the composition is invariant. And also, this exponent allowed to be the minus infinity. So perhaps we have that lambda f is equal to the minus infinity. So now lemma 1 combined with lemma 2 gives us the oscillator's theorem, because we can apply the first lemma to find we can find either subbundles, or we are done with the proof, because we have in our bundle the vector's growth in the same way. Either we have we can find the subbundle E and continue apply this lemma for the V with this quotient space. Yeah, and we have the filter, and we don't get the filtration. We need to apply lemma 2 to rearrange our subbundles to be a proper filtration. So I think I can erase the lemma 1. So, as I mentioned, we can find the subbundle E. After this, we can check if quotient space vectors growth in the same way, and we can apply this assumption to E and repeat this process, and we can get these numbers, the ripon of exponents. And if we find some E prime space, the subbundle, so if lambda prime for this space, so this is the number that our vectors growth in the lambda E prime, in the E prime, and if this number are more than E1, we are done, because we place this in in the beginning of our filtration, and it will work out. Otherwise, we can apply the second lemma where we should apply in this way. And we need to, and via this lemma, we obtain our splitting map sigma. Yeah, this goes from our quotient space to other quotient space. So this our E prime. And then the pre-image of the quotient space E under the projection V to V, or the quotient space E and 2, and it gives us a subbundle denoted as V with exponents lambda 2 that will grow, that the vectors will grow with lambda 1 rate. Yeah. And yeah, no, the vectors outside of this bundle will grow with the rate lambda 1. And secondly, that let me write here. No, better to left here the lemma and continue in the left part of the desk. Okay, maybe not. Okay, let me left here the sequence. The our short exact sequence. So, firstly, let me rewrite this statement. Вот я сейчас перепишу. Firstly, any vector v from outside of our bundle v that have with exponent, subbundle with corresponding exponent 2 will grow at lambda 1 rate. Secondly, our subbundle with exponent lambda 2 will maps naturally naturally to the quotient space V to the E, which has exponent lambda prime. So we can then we iteratively apply our second lemma to the we apply the second lemma iteratively to the sub-bundle that corresponds with lambda 1. And we can apply this process until we have the lambda e less than lambda prime. It's like we move from our filtration, our new subbundle, then we can find the right place, and the right place, it will be the moment when this inequality are true. So I think I don't have time to prove these lemmas, so this is the end. Александра Сергеевна, ну, по времени я уже не успеваю доказать леммы.
Ну, я думаю, что вы можете технически какие детали пропустить. Если она идейно важна, то вы можете про это сказать два слова.
Окей.
Если это просто техника, одинаковая,
Ну,
можно,
so let me, in the end, the state of the plan, how we prove lemma 1 and lemma 2. I'll leave it here. I will erase the second lemma. Okay. So the idea of the proof of lemma 1 is to get the projector space of our bundle V with the projection P on our space. Then it is first. Then we know we can find in this the space of the measures that we defined like this. So it's all measures new that under the instruction P goes to the mu. So, and which is important to say, the Krylov-Bogolyubov argument, let me state it here. From the space, we need to find nu that minimize the function defined like this. Yeah, it from our projective space of vector bundle V to the R, and we take the and we define it like this. T omega T V, and the integral of our f will goes to the from the measure spaces. I will denote it like big mu that goes to the R. In other words, we take the measure nu that goes to the integral for our projective space f, and we integrate by this measure. So we find the nu that minimizes this integral, and the argument here that we can find such nu minimizes this integral, and moreover it is a measure that gives us the one second. And this measure will be the ergodic, and nu the yeah as already said. So we now apply the Krylov-Bogoliubov argument said that we can find such, and the next step to apply the Birkhoff theorem for the f. So we can find the some bundle E, and secondly, for prove this lemma, we need to if we find such subbundle, we are done, we can and we drop into the two variants. Let me state it here. Let me state it here. So we drop into the variants. The first is E not equal to the V, so we find such some bundle. Secondly, if E equals to the V, we state that the vectors from growth at the same, we construct E with the notion that the vectors growth at the same rate. So in the end we get that if E not equal to V, so we find the subbundle. So we drop into the second point of the lemma. Or if we find E and E equals to the V, we're done, because we can state that the vectors from our bundle growth at the same rate. So, and for the proof of the second lemma, I'll erase this. So we pick proof lemma 2. Firstly, we pick the transformation, the map sigma 0 that goes from the F to V, such that V is equal sigma 0 F. So our transformation we can write here T, Tf, and U. And we have by the restrictions, we can say that, and yeah, we want to find the splitting map. So the splitting map will be will differ. The splitting map will differ from the sigma 0 by this notion. So we can find mu tau that will, we can write it like this. So the tau is a map from F to E. So, and yeah, and on these statements we can write the equation that gives us that the tau the tau omega is equal to minus the infinity sum of t n plus 1 e omega composition with two operators t and omega t and f omega. So to see how this behaves, we can write such omega t and omega. So we have the subbundle f that goes to here, f. Then by this transformation, it goes to the E, and with this information, its E goes here, and we stay in this layer, in this fiber. So technically, we can calculate the norms of these operators, and yeah, this is the calculation solution, and our sum converges not to infinity because we can calculate the operator's norm, and it will be and this will be the argument why the growth not so large, so it converges. And where this transformation, we find the transformation that splits our short executive sequence. So that's all.
Thank you very much. Are there any questions? So maybe on the first glance it looks to you a kind of artificial statement and it's unclear how to use it. But in reality it's extremely powerful tool. I will provide you just a couple of examples where this tool is very useful. Thank you. The first example is related to what we discussed previous time when we were talking about layers and interchange transformations. So I told you that interchange transformations are closely related to the measured foliations on surfaces. And locally the picture looks like you have an oriented surface and you have a one form and it's on the surface, so it's a line surface. There is a one form and this one form defines you the foliation on the surface. The foliation locally looks like a cut bread if you want, because what you do is that you fix the linear flow on this surface. That's the same thing. And you have some singular points on the surface that correspond to zeros of your one form. And so these points are saddles. And then what I want to say is that there is a natural way to to associate some kind of renormalization procedure with the interchange transformation. This renormalization procedure will recall a lot the Euclid algorithm. And so it will be coded by some cocycle. And so the Laplace exponents of this cocycle, the one that we define due to oscillated theory, will be responsible for the speed with which the leaves of your foliation approach so-called asymptotic cycle. So what is the asymptotic cycle? You have the surface, and as I said, you have a one form. And due to Poincare duality, you have a duality between the one forms and the cycles of the surface, the elements of homology groups. So the element that corresponds to this one form is exactly the asymptotic cycle. And so this Lyapunov exponents of some easy defined cocycle that you can define without any understanding of topology or something, they will be responsible for the speed, how fast the leaves of your foliation glue to this asymptotic cycle, how do they rotate around this asymptotic cycle. So they have very deep topological sense. And one of the results that Arthur Eiler approved, I showed you the first one for which he was awarded the Fields Medal, this weak missing statement. There is another example of his result, it's his theory with Marcelo Viana, where they showed that all the Lyapunov exponents of this cocycle that I'm talking about, they are different from each other. And so it gave us a kind of much deeper understanding of the topology with this foliation and so on. So this is the first application. And another application was the following, that as I said, this renormalization procedure looks a lot like Euclid type algorithm. And you can define more generalizations of the Euclid algorithm. Namely, you can define so-called multidimensional fractional algorithms. When you try to approximate not one number, for instance, with rational numbers, but a vector. And a huge family of these algorithms can be described using the terminology of the cocycle. And the Lyapunov exponents of this cocycle will be responsible for the convergence speed of this multidimensional fractional algorithms. So they will tell you how fast your algorithm converges, how good it is in the sense of approximation. And the study of the properties of these Lyapunov exponents that you define using the oscillated theory provides you a deeper understanding of the quality of your Diophantine approximation. So things that look kind of very artificial, in reality lead you to a very powerful tool in many geometric or number theory problems. They allow you to apply some techniques from dynamical systems to the problems and related subjects. Вы определяете с помощью теоремы осцилляции, а дальше уже свойства их вы изучаете с помощью всякой другой техники, например, вот, то, что придумали Артур Марсаловян, и эти свойства имеют понятную какую-то интерпретацию либо в терминах теории чисел, либо в терминах топологии, иногда той же самой динамики, когда вы изучаете гиперболическую динамическую систему, вы определяете показатели Пумова, то это вы можете определить, как она себя ведет в окрестности особых точек.
Так, все, батарейка есть?
Да, все тут есть.
Сейчас. Так, слышно?
Если там зеленая полосочка болтается, то 100% есть.
Так, меня хорошо слышно или? Ну, вроде болтается, но надеюсь, что...
Сейчас давайте на записи проверим.
Раз. Мгм. Мгм. Да, я знаю. So, let's start. Today I want to talk about different approximations on manifolds and flows and the connection with the homogeneous or flows on homogeneous spaces. Homogeneous, thank you. So, I want to start from very easy statements, but I think it's very important to think about simple things before we start. So, one very important notation. I will write think as a minimum of these two values, q and 1/2 minus fraction part of q. What this is a distance between q and integer numbers. If we have a graphic of this will be I will write this in the sense distance between the nearest integer number. So, and let us consider some vector alpha sub 1, alpha sub 2, alpha sub n belonging to the raised to the nth power, Rn. So, first question. Does anybody now answer on this question? So, I'll write this estimate here. The minimum of all integers from 1 to n of q I eta of this value. So, q times alpha sub e, q raised to the c. So, does anybody know which c can, some values of c, for instance, question, for which values of c we can say that there are an infinity set of solves of this inequality? Does anybody now answer on these questions? So, for which c, we know that there is a infinity set of such q. For instance, c equals 0 is obviously correct because there are a lot of q such that this is value less than 1. But does anybody know more strong result, something non-trivial? No. I repeat my question. Find some c such that this inequality has infinite many solutions. That's
Maybe something like 1 over n?
yes, 1 over n. First theorem is directly a theorem, theorem 1. It's very easy but very important for start theorem. We states that there are an infinite set such inequality. So maximum, of course, it's mistake. Maximum, minimum is not interesting so much. Maximum of q alpha sub y is less than 1 over q raised to the 1 over nth power has infinitely many solutions. Many solutions. And q belonging to natural numbers. Does anybody know proof of this fact? It's a very easy fact. It's just Dirichlet principle. So it's very easy fact. So I think I can give a proof because it's so short and so simple. I think it's something easy.
What do you assume about alpha?
Alpha, it's maybe alpha eta. It's some real numbers.
Not necessarily irrational.
Yes. I will give a very short proof of this fact. Let us consider some set. The set is look like x is some real number, and y, this is some vector. It's a vector in Rn plus 1, and this is not and x is less than some q raised to the n minus q, minus q raised to the n is greater and less than q raised to the n, of course. And max 1 over E over N x y E minus y E is less than 1 over Q. This is some body in R times, or in the Rn plus 1. I will try to draw it, but it's so difficult for me. It's like a sort of parallelepiped. Sorry, it's like a sort of, but it is not. So it's is it clear that this is a convex set? Is it clear? This is a convex set. Yes, it's convex set. It's symmetric. It's central symmetric set. 0 is the point of this set, belongs to this set, and you can calculate volume of P and check that is 2 raised to the n plus 1 power. It's very easy facts about P. It's convex. You can check it explicitly by definition. If some point belongs to this body, then the minus point belongs to this body, and the volume of this body is just 2 raised to the n plus 1. And that's a very famous theorem, Minkowski's theorem, Minkowski, which states that if we have some body V in R times N such that V is convex to X belongs V if and only if minus X belongs to the V, and volume of V is greater than 2 raised to the N, or volume V is greater or equal 2 raised to the N if V is compact. So this is obviously compact. So if we know these 3 facts about body, then there is P belonging to V and Z times N. We have points with integer coordinates in this body. So, thank you. The same. So, and we know then our P is convex, is symmetric, and has volume 2 raised to the n plus 1, because we not in Rn, but in Rn plus 1. Да-да?
Извините, в каких случаях у нас в теореме допускается, что объем больше либеральный?
Ну, вообще говоря, теорема формулируется вот так, но если вдруг мы знаем, что дополнительно, что тело компактно, то мы можем, в принципе, попросить, чтобы равнялось ровно, строго. Это такая теорема. So, due to this theorem, we know that there is some integer point, does not 0, in this set. But this, what we want, because it's less than 1 over Q, it's big number. It's big number. So we know that there is some point. So from this statement, we know that there is some point x0, y0 such that Q, x0 alpha, wait, minus 0y is less than 1 over q is less than 1 over x0. So that's all. But now we consider q raised to the nth power. So if we want to, so if we say about some number less than q, we need to write here 1 over n. So this is just a Dirichlet theorem. It's a main and very simple result of Diophant theory. And I want to start with that. Why? Because we have some other sort of results, which called metric Diophant results. This is such that and Hintschen theorem states Hintschen theorem. I don't know the correct right of spelling this surname in English. I suppose that's Hintschen, the famous Soviet mathematician. So what's stem? Suppose that C of Q from N to R is bounded. And does not grow. C of Q and suppose that if sum of C of Q over Q from 0 to infinity converge, then almost everywhere, raised to the n power, vectors alpha belonging to the R times n is badly approximate. What I mean by this fact, it means that this inequality has only finite set of solution. So we know that there are a lot of solutions of such inequality. But if we have some convergence series, we will not have a lot of solutions. For instance, let C of Q be such that 1 over Q1 over n times logarithm of Q plus 1 and all in the 2 over 1. What we know? We know from Hintschen theorem that this series is convergent series because it's just 1 over Q logarithm of Q plus 1. This convergent series, of course. So we know that there is only finite many solution of inequality max of Q times I sub E less than 1 Q1 over N logarithm of Q plus 1 to the N. So what we know? We know that the typical number for
Sorry, why do you assert that this series is convergent?
Сейчас, я вроде бы правильно подобрал. Сейчас. Because we have such integral.
squared. It is squared. That was just a mistake because this integral converges. Sorry, I don't write. I write 2 here and here, but don't write it here. Sorry, that was just a mistake. So what we know from this? We know that we have a lot of solution of such type, but if we write something more than 1 over n, we will have no solution in some sense. And now we can, but this is almost everywhere. But I want now. We can consider different approximations on manifolds. What I mean? Suppose that we have some manifold. And I will start from very simple manifold. It's something like that. Very simple manifold. What I mean by manifold in this sense? I have some subset of I have some subset U of R, it's just some interval, for instance, and I have a function from U to the R squared, and this is just function of this, that's T squared. Very simple manifold. It has 0 measure in there too, it's just one-dimensional manifold, but what we can say about measure in sense of U, in U we have some typical Lebesgue measure, of approximation of points, but not in U, in R2. So let's formulate it more explicitly. What we can say, for instance, about measure of such points x belonging U, such that such an equality has infinitely many solutions. What we know? We know that in, this is a more interesting question, why? We know that in all space, typical point has not many solutions for this inequality, but we can consider a measure of points in U such that the measure, such that the images where alpha sub e is just an image of x point. So we want to talk about points on the manifold, not in the U. And it's more interesting for us. And today I want to talk about connection between these approximations and dynamics on homogeneous spaces. Вот. Ну, еще раз по-русски повторю на всякий случай, что вот в чем идея. Что вот я объяснил, что в целом во всем пространстве хорошо приближать точки мы не умеем. А теперь мы что говорим? А давайте посмотрим на какое-то многообразие и посмотрим, как много можно приблизить его точек, но не померив во всем пространстве, а вот по внутренней мере. То есть насколько хорошо они приближаются изнутри как бы. Мы же его как-то так вложили. Вот, и мне кажется, что это, в принципе, интересный вопрос, потому с одной стороны, с точки зрения теории чисел, с другой стороны, тут довольно явно будет показано, как здесь динамика проявляется на потоках. То есть покажу, что вот хорошая приближаемость в каком-то смысле это то же самое, что стремление на бесконечность некоторого потока. So, it's time to give some definition. Definition 1. Suppose that we have some point in R raised to the nth power in Rn. Y is very well approximable VWA. If there are infinitely many solutions of inequality max y from 1 to the n q I y less than 1 q raised to the 1 plus epsilon over n for some epsilon. For some epsilon greater than 0. It's, we proved that the measure of these points in Rn is just in 0. Yes? Sorry. Alpha, and alpha is just alpha sub 1, alpha sub n. Sorry. Thank you for question. It was an important question. So that's definition. And one more important definition. It's more strong result. Suppose that's alpha some point of R sub n. Alpha is very well multiplicative approximable. I'll write such letters if there are infinitely many solutions of inequality multiplicatively approximate. We haven't some so we have here not maximum, but the multiplications of all values. So we know that point, it's always less than nth power of such numbers. So point can be very well approximable, but not very well multiplicatively approximable. So, and most important definitions of our talk is definition of strong extremal at strong extremal manifold. Definition 2, oh, sorry, 3. M is some smooth enough, analytic, it isn't important, manifold. So M is extremal if and only if almost all points of M in sense of inner measure on M are almost points of M are not very well approximable. So we will call some manifolds extremal if almost all points of this manifold is very bad approximable, not very well. And the definition 4, it's M is strong extremal if and only if almost all points of M are not very well multiplicatively approximable. So, the main results, it is not direct branch of math. There are a lot of modern results, and I want to talk about Kleinbock and Margulis result, such that I need one more definition. I hope this will last definition for today. F is some function f from U, some subset of R times D to the Rn. It's sum is M-bending, and X some point of U. X is not right if there exists L such that R times N can be spanned, can be represented F span of D K D X1 K1 D K M X, sorry, and here the key D XD of F, where K is some numbers less than L. That's the definition of some non-degenerate point. Вот еще раз повторю, что вот у нас есть какое-то выложение. Да, прошу прощения. То есть вот у нас получается, что Rn может быть представлена как линейная оболочка производных порядка не выше, чем L. То есть так вот натянули. And now the main result, I think we can write it here. The main result is such that so suppose that F is ну, вплоть до L, да. Да. Ну, в какой-то точке,
Нет, в точке я понимаю, что я говорю, что мы либо в какой-то момент для какого-то либо получаем все пространство,
Ну,
либо никакой момент не получаем.
да, ну, все-таки давайте так предположим, что F принадлежит классу CM, и N меньше, чем M, да? Не будем совсем уж разбегаться. Ну да, ну вот, предположим, что так уж у нас случилось. Что даже вот введем ограничение, что пускай оно даже CM гладкое, вот пускай так, да, то есть не обязательно бесконечно гладкое, то есть не обязательно бесконечно будем множить. Вот пускай у нас удалось до порядка M получить все-таки. Вот рассмотрим такой случай. Ну, на самом деле, не очень вырожденный случай, то есть понятно, что это что-то типичное довольно. So, let F1 F1 is embedding of U to Ln, and almost all points of U is not degenerate. So suppose that we have something like that, and I want to write from this definition that all almost all points of U, sorry. Then we know that M is strong extremal. So from this main result of our talk, this is a result of Margulis and Kleinbock. Let us consider some example, for instance. We have some curve, for example, t squared, t raised to the n. It's some curve.
Сейчас, а f от каких переменных зависит?
От переменных v, это какое-то подкрытое пространство в RD, и f зависит вот от координат там, и, кстати.
У нас есть домерная
Да, конечно, да. 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 Вот оказывается, что если так выполнено, то все точки в каком-то смысле плохо приближаются. Ну, почти все. And some example, we can consider such curve. For example, n is 2, t squared. What we know about points? We have first derivative is just 1, 2 times t. Sorry, which example I was right here? Not such that. We will have some more interesting example. We have in some curve f of t. First derivative is 1 f prime of t and 0 second derivative of t. So suppose that second derivative of f is not 0 almost everywhere. It means that the curvature of our line is not 0 almost everywhere. So from this fact we know that this curve is strong extremally almost everywhere. It's strong result belonging to Spring-Zhuka, I think. It is not obvious. It's very strong result. It's so what time? Сколько сейчас? Ой. Ну ладно, попытаемся чуть.
Мы договорились, что в следующий раз тоже попробуем.
Да, хорошо, тогда не буду спешить.
Не форсируйте.
Да. Ну, вот, так, давайте так, пока понятно, вот к чему я клоню, какие основные результаты. Ну, все, отлично. So. A few words about space of lattices. We need to say it to thinking about of approximation like a flow on space of lattices. So, space of lattices. Second part, space of lattices. Space of lattice. So, suppose we will consider only unimodular lattices, that's lattices with one covolume, with covolume 1. So, it's a well-known fact that lattices it's well-known fact that omega is just SL n of R factorized by SL n Z. It's well-known fact. It has a finite Haar measure. It was proved for n equals 2 in this course, but it's correctly in all dimensions. And this is not compact. So we need some compactness criteria, like an Arcelor-Scully or something like that, for this space. And there is a Mahler's criterion of compactness theorem. So suppose that we have K, some subset of omega. K is compact if and only if exists some epsilon greater than 0 such that for all lambda belongings to the K, infimum of length, it is not the distance between number and nearest integer number, is just a norm in vector space. Infimum for V belonging to the greater than epsilon. So what states this theorem? That there some set is compact, some subset, if and only if it does not contain some short vectors, very short vectors. So that's Mahler compactness criteria, and we will discuss about approximations. And
You mean the lattices I emit
don't contain short vector.
the subset
Mm-hmm. So it's a subset, it's a set of some lattices. It's covolume 1. And we say that some K is compact if and only if every element of K does not have very short vectors.
And what if we take a compact subset and get rid of some point of this subset?
Sorry?
Взяли мы компактное подмножество и выкинули из него точку.
Ага.
Вроде это критерий не нарушился.
Выкинули из него точку.
И что, произвольно выбрасывать точки
Сейчас, нет, мне не нравится тоже. Сейчас. Давайте пускай К будет замкнуто. Closed. Да, все, да, спасибо. Thank you. So, what about approximation? For start, I need one more theorem from number theory, the last one. It's Hinchin theorem. As you remember, I wrote before something about maximum of Q. What does it mean? It means maximum of 1 over n modulo QIE minus PE. And this is an arbitrary PI. But I can write something. So what it means? It means and the PI is nearest number. And we have one Q. But we can write something else. We can write something like that. Sorry. We can consider some forms. This is scalar product. And I want to say some equivalence statement. So, Сейчас, минутку. Мне хочется аккуратно переписать просто. Сейчас. Сейчас, минутку. So, I want to give equivalent definition, theorem. It's Hinian theorem, some sort of Hinian results. Alpha is very well approximable if and only if some inequality have infinitely many solutions. Sorry. So, alpha is very well approximable vector if and only if such an inequality has infinitely many solutions. It is not obvious. It is not the same. It is not just a definition because in first definition we had one Q and a lot of P, but now we have a lot of Q and one P. And this is equivalent. It's Hinian transference principle. And alpha is very well multiplicatively approximable if and only if, sorry, so it is not obvious result. You can find something like that in very good book, Introduction to Idiophantom Theory by Castles. It's transference principle. Is it clear? Well, the statement, not proof. It's very hard.
Можете, пожалуйста, повторить
Ну, максимумов из куитых и единичек, видите ли, там часть куитых может равняться нулю, в принципе, и чтобы это исключить, здесь, да, куиты точно не нули, потому что мы здесь убираем точку 0,0, вот здесь можно убрать точку 0,0, и понятно, что тогда куиты не могут быть нулями. Вот. И получается такой вот результат. И сейчас я попытаюсь объяснить, как это связано с решетками. Now we will talk about connection between lattices and approximation. So, let us consider some lattice. Some lattice. Some lattice. Lambda is sorry, is just ID n. This is a lattice in Rn plus 1. It has some points. It has P plus Q1 Y1. Also, I think. that's the points of lattices, of our lattice. You can calculate this explicitly. And y is some vector from Rn. It is not. It's like an alpha here. So we can consider these lattices and main lemma. Main lemma, lemma 2. Oh, sorry, lemma 1. Sorry. If y is very well multiplicatively approximable, then there is some gamma greater than 0 such that exists infinitely many T belonging to R such that, oh sorry, one more definition to be clear, we have a geodesic flow GT of this form ET E minus T1 E minus T sub n, where T is a sum of Ty from 1 to n. So we have some geodesic flow. And delta of L is infimum of lengths of vectors belonging to the lattice. These two notations. So if there are many so I will write T without bar. This is a number. T with a bar is a vector. Such that delta of GT so this very important lemma, what it states, if we have very well multiplicatively approximate point in Rn, then the flow, then our lattice goes by flow to the infinity. Because we have a Mahler criterion of compactness and bounded, and we know that from this criterion, we know that if point is very well multiplicatively approximable, then the flow will go to infinity when it will act on this lattice. Is it clear? The statement, not this proof. То есть, еще раз по-русски продублирую, что я говорю следующее, что если у меня точка вдруг оказалась хорошо мультипликативно приближаемой, то тогда оказывается, что вот действие геодезического потока на пространстве решеток будет стремить ее к бесконечности. Вот наша основная задача теперь уже не изучать какие-то непонятные диафантовые приближения, а просто изучить вот поток какой-то решетки, ну не абы какой, конечно, то, что какой-то решетки и понять, идет он к бесконечности или не идет. Ну вот я объяснил, что вот у нас был критерий Маллера, что вот подмножество компактно тогда и только тогда, когда оно не содержит слишком коротких векторов, да? А вот у нас тут получается, что вот можно найти такие моменты времени, что у нас вот эта решетка содержит очень-очень короткие вектора. Я могу вот взять вот эти моменты времени и заполучить множество k решеточек, да? Ну или просто взять объединение по всем t. Да, то есть и он у меня будет, получается, все дальше, то есть у меня не будет ограниченности в пространстве решеток, он будет все дальше и дальше забегать на бесконечность.
То есть если вот прямо далее нам будет хрен, а здесь, соответственно, мы утверждаем, что, ну, то есть, что там будет происходить за какое-то фиксированное время вращение. Здесь мы как раз утверждаем, что...
Да, что... То есть я поэтому решил рассказывать, потому что вот есть вроде бы чисто теоретико-числовой вопрос.
Нет,
да.
у меня
Да, конечно, слушаю.
Другое утверждение, что что-то стремится к бесконечности, означает, что есть какая-то бесконечность, которая...
Не, это он не пишет стремиться,
Нет.
что он не будет возвращаться, что он будет уходить в свою жизнь.
Нет, имеется в виду, что вот, давайте я так скажу лучше. Вот критерий Маллера дает нам понятие ограниченности. Вот что значит быть ограниченным на этом странном пространстве? Он говорит, что вот если есть такое эпсилон, что в семействе все вектора не больше эпсилон, да, ну точнее нет слишком коротких векторов, короче эпсилон, то множество у нас ограничено. А вот это утверждение говорит, что у нас поток не будет ограниченным, что он все дальше и дальше будет заглядывать в какие-то моменты времени. То есть он будет как-то так вот, бесконечность уходить, не стремиться уходить. Вот. Да, вот в таком смысле, да, не стремиться, спасибо за корректировку. Вот, я думаю, это вот такой очень, такой динамический результат, чисто. Но мы отошли от теории чисел, теперь можем изучать чисто потоки. Это не совсем проблема Оппенгейма, но что-то в духе того, что делал Маргулис. Это, собственно, и делал Маргулис. So, and now we will prove that typical points has bounded trajectory by action of flow. But for start, we will try to prove lemma sub 1. What's time? Oh, no.
You have like 10 more minutes.
Okay, so I think I will prove only lemma 1, and I will prove today why typical point is not very well multiplicativity approximable. I think I will prove in the next lecture, why typical point has not the same behavior, why the trajectory of typical point is bounded. So, we'll try to prove this by lemma 0. Lemma 0. It's so technical, but it's some sort of interesting result, I think. So, suppose that epsilon is some zero greater than is some number greater than 0, and y is some element of R times n, and PQ is some point belonging to the n plus 1, and y is very well multiplicativity approximable. Then we will write R is just product of y from 1 to 0 maximum of 1 and model of qy, and this all raised to the minus epsilon over n plus 1. And we will define t sub y as logarithm maximum of 1 and qi over r. It's moment of time. It's some moment of time. And I want to prove that, and gt is just a matrix t minus t1 in minus tn, where t is sum of t sub e. So I want to say that at this moment we will have what we will have. We will have d delta of t lambda sub y is less than r. So it's it is not arbitrary number. It's number such that and p and q such that obviously what I want to write here, I want to write here that qy minus p is less than 1 over p maximum of 1 qy raised to the 1 plus e. So we will consider such points, p and q, not arbitrary, and I want to say that at these moments we will have very we will have very small number. It is not exponent as in lemma 1, but now it is not exponent. But this is very small number. I will prove this statement, not this, and at the next lecture I will prove lemma 1. Is it clear? То есть я докажу не вот это утверждение, оно почти мгновенно будет следовать, а вот некоторое более техническое, что я просто вручную найду те моменты времени, когда у нас вот все это произойдет, все это схлопнется. Вот. А в остальные моменты времени, ну что ж, ничего не поделаешь. Sorry. So. It's so technically, but I think one technical moment is not so hard. So, let's write the points of lattices by action of this flow. Gt of lambda y, it's what? It's e to the t one sorry. So, we will have such lattice. So,
Вопрос. Там умножение идет e в степени t-1 на q1 или...
не-не-не, да, e в степени минус t1 умножить на q1. То есть у нас вот такая решетка. А теперь просто убедимся, что в ней действительно нет слишком коротких векторов. Что в ней оценку на самый короткий вектор. Да? Точнее так, что в ней наоборот есть короткие вектора. Убедимся сейчас. We will check that this lattice has short vectors. So, what means to have a short vector? So, we know that E minus Ty times Qy is less than minus maximum of Qy and 0. And from the definition, we have that what does it mean? We have such definition. So it's E minus logarithm of maximum 1 over Qt over R times maximum of 1 and modulo of Qy. Oh, it's just an R. So these coordinates are short enough. So let us consider first coordinate. If we will prove that this is short enough, we will prove that all coordinates short enough. It's so we will multiplicate max 1 qy y from 1 to n. And what is it? We know from this that from this equality, what we know? We know that r times e raised to the te is just maximum of qy and 1. So what we can say about this product? It's just r raised to the n and e raised to the t, because the sum of t sub e is just an et. It's just an quality. It is not hard statement. And we know, and on the other hand, we know that y is very well approximated. So we know that the qy plus p is less than 1 over p plus q raised to the 1 plus e. It's just a definition of, so it's corollary from Hindchin transference principle and definition of very well approximable numbers. So we have there from statement of our lemma, and we know such quality. So from this we write e to the t qy plus p less than e raised to the t, and we know that this quality, what I mean by p plus q is this is just p plus q, only for shortness, only to be short. This is just this product. But we know that this product is just r raised to the n and e to the t. It's just r to the n, e to the t times product plus q raised to the epsilon. But we know such. But what is it r? R, it is not arbitrary number. R is just p plus q raised to the minus epsilon n plus 1. It's just a definition of R. From this theorem, it's just definition. So r raised to the nth power, it's what? It's p plus q raised to the minus epsilon n over n plus 1. And this is just p plus q raised to the minus epsilon times 1 over r. You can calculate this explicitly. So, sorry. Is this what I need? And from this, we know that this is just an R, explicitly, from this quality. So, I think we can stop here because I'm tired and because it's time to stop. I think that's all. Does anybody has any question? Oh, no. That's
Okay, next time we will continue with Viacheslav's talk, and then Sani Krasovskaya will tell us about transfer operator and the connections between dynamical systems and analysis.